Okay. Thank you. Thank you for your patience. I think that we've got things hooked up now, and so we'll go ahead and get started. All right. Again, this is Fume Hood Management, Maintenance, and Testing. We've got a pretty good amount of information to cover in the next couple of days. A little bit about 3-flow just to get us started. We focus on ventilation for indoor environments. The majority of our work is in laboratories and critical workspaces, and our mantra is the right flow in the right place at the right time. And we've been doing this for over 26 years. And so we have a lot of experience working with all kinds of different systems and encountered a lot of different problems. And hopefully some of this information will help you able to identify and alleviate some problems and make systems operate more effectively and more efficiently. We've had a great opportunity and been very blessed to have had an opportunity to work with a lot of great organizations around the world. And we've learned a lot from these different organizations, a lot of creativity that comes to lab ventilation and lots of different types of fume hoods. And so we're going to try and cover a wide range of topics here so that you have a lot of ideas about how the systems function. My background is I started testing fume hoods when I was 18 years old. I was a stay-in-school student. I was assigned to work with the federal government at the National Institute of Environmental Health Sciences in Research Triangle Park. And while I was there, I got my undergraduate in mechanical engineering as well as a graduate degree in industrial hygiene. And since that time, I've had an opportunity to work on various different committees for ventilation standards for safety and health. So this presentation will cover some of those topics, and you may see some old stuff, but some new stuff as well. So our learning objectives is to really understand how modern fume hood systems are designed and operating. We're going to look at what factors affect performance. You should be able to understand how these factors influence the ability to contain and protect people from exposure. We're going to look at the different tests that are required to evaluate fume hood operation, as well as how well they're performing. We're going to do some diagnostics and some troubleshooting to look at how do we identify problems and then implement remedial measures. And then finally, talk about a lab ventilation management plan that kind of pulls it all together and will give us the tools to ensure that it's functioning properly. So we're going to start with a discussion today on the modern airflow systems. Then we're going to talk about standards and guidelines. Then move on to the lab and the fume hood tests, follow with some diagnostics and troubleshooting, and finish tomorrow with the lab ventilation management plan. Now, we have both a series of slide lecture type of format today, and then we're also going to go into the lab and look at some hoods and see how they operate, and we'll look at some videos of different operational scenarios. So hopefully it'll give you a wide range of experience to better understand how these systems are designed and operate and need to protect people. So our course agenda for today, we're going to start with our introduction. We'll move on to the fume hood systems and standards. And then around 2:30, we're going to take a 10-minute break. Wouldn't expect you to be able to sit still for that length of time. And then we're going to come back. We're going to talk about how to test the operation of a fume hood. And then we're going to do some demonstrations in the lab. And so at the end of this session, we should have some time for questions. Feel free to put questions into the Zoom meeting down there in the questions and chat section, and those will be compiled, and we'll try to answer them as we go along. Tomorrow, we're going to, in day 2 session, we're going to do a quick review of day 1 topics, and then we're going to move on to fume hood performance tests. And we'll show how to differentiate between what's an operational test and a performance test. Again, we'll take another break about midway through, and then we'll do a fume hood demonstration and follow up by implementing the ventilation management plan. So as I mentioned, in your control panel, you may be more adept at running it than I appear to be, but in what you can do is on that control panel, there should be a section for Q&A and chat. If you open that up, you can enter your questions there. They're being monitored by Gary and Carrie. So hopefully we'll get those questions and be able to respond directly. All right, so our very first poll question here, if I can manage to get this to work for us. Okay, our first poll I'm going to launch it. And okay, so the first question is, how would you rate your knowledge of fume hood systems as an expert, advanced, proficient, developing, or novice? All right, if we just take a moment there to input your answers, that'll give me an idea of where we're working. And then our second question is, what is the minimum safe average face velocity? So first question, how would you rate your knowledge of fume hood ventilation systems? And the second question is, what is the minimum safe average face velocity? All right, looks like we've got pretty much nearly all the respondents at this point. We're pretty close anyways, 90%. So I'm going to go ahead and end that poll. And oh, we got 100%. Fantastic. Okay, so let's take a look at the results here. I can share those. And so our results indicate that we have about 45%, the most in our one developing, which is great. A lot of good material here, proficient, and even the advanced will have a few things for you as well. And then as far as the minimum average, safe average face velocity, the majority of people said 100 feet per minute, but the equally said it depends. And so we're going to see that the right answer there is it depends. Okay, let's stop those results, and we're going to move right on to the next part of the presentation here. All right, so starting at the start, research is serious work. And what I mean by that is that the organizations that do research or new product development spend tremendous amounts of money building laboratories for the singular purpose of enabling the potential for research success. Many organizations, their reputation and their future success is based on the outcome of research. So the building a laboratory is specially designed to provide environments that support the occupants, that actually increase that probability of success. And we recognize that there's going to be use of many different type of hazards in those laboratories, and so we have to have the right type of exposure control devices to protect people from exposure and protect our most valuable assets in the lab. So there are many different types of laboratories, whether you're working with chemistry or biology or maybe radioisotopes. A lot of work that's going on today in nanotechnology. That's a particularly worrisome area because the materials are so new. We don't have a lot of toxicological or physiological information on the risk associated with nanoparticles. And so making sure that we have adequate protection is going to be really important so that we don't look back retrospectively and say we didn't provide adequate controls. And then we have teaching labs and a lot of maker spaces where they're working with 3D printers and a lot of different potential for creating fine particulate that may have some hazardous properties. And then we have a different environments. We have clean rooms and then animal vivariums. And so in each of these spaces, we're going to have different functional requirements, different requirements for cleanliness, different requirements for temperature control, pressurization, and so forth. And that plus the need to protect people is the risk. So if we add the risk and the functional requirements, that equals our demand for ventilation. So labs can be dangerous. When we look at laboratories and the type of work that goes on, whether they're working with chemical hazards or biological materials or radiological or combinations of materials, we need to use the ventilation systems to help protect people from overexposure. We also need to look at the potential for physical hazards, whether there might be a fire or explosion. And I can tell you that from experience that an explosion will ruin people's day. So we want to make sure that we avoid that type of scenario, and we're going to do so by understanding the risk and then properly optimizing the systems to protect people. So risk can be a function of many different factors, but it generally will range from negligible to extreme. And what's at risk really is first the occupants themselves. If we don't do our jobs correctly and ensure that the systems are able to protect them, and they don't use those systems properly, they're at risk of being overexposed and suffering some adverse health effects, even death. And then there's the liability issues. Some of that stuff does go downhill, and there may be responsibility assigned to people. So we want to make sure that we're doing the appropriate job. There could be damage to the property and the environment, materials getting out into the environment, and then the subsequent impact on the research itself, the failure to meet the mission or the research objectives. And so all of these things can add up. And then we can also look at an improperly operating system is going to use excessive energy and be wasteful. So we want to be good environmental stewards. We want to protect our occupants. We want to meet the mission of the facilities. And so we have to look at the ventilation systems as a mechanism to help us accomplish these objectives. Now, when working in a laboratory, because of the potential danger and the need to have appropriate work practices, we have to be trained. And that means we have to follow these rules in the laboratory, make sure that we have the appropriate personal protective equipment, and we're using appropriate safety practices in the lab at all times. And that starts first with understanding the type of work that's going on in the space. Communicate with the occupants. Make sure we understand what type of work are they doing, what is their objectives, how can we help facilitate that work and create a better opportunity for success. And it's about understanding their processes and their hazards and their environmental control conditions so that we can manage the systems to meet those needs. Now, when we look into a laboratory, this is obviously a scene from Breaking Bad, the movie or a TV show, but what I show here is that inside, behind those closed doors, may be activities that we don't anticipate. And we need to understand what's going on in the laboratory so that we don't enter a space or potentially contaminate a research project. And so knowing what's going on, really critical to make sure that we are, one, protecting the occupants, we're protecting ourselves, as well as two, making sure the facilities are supporting the needs of the occupants. Oftentimes, we'll have signage on the doors, and that will tell us a little bit about what's going on. It may tell us the occupant and the type of activities. There's pictograms oftentimes that tell us a little bit about what kind of hazards might be encountered beyond that door. And so clearly when we look at these, it could be toxic chemicals, it could be ultraviolet or flammables. And then we have the first responders diamond, which tells us not only the type of hazards, whether it's a health hazard or a flammable hazard by its color, but then we also have a numeric representation of the magnitude of that hazard. So these are signs and so forth that we should be familiar with so that we understand the type of activities that are going on in the space. From our own standpoint, walking in the laboratory, I've been in thousands and thousands of laboratories all over the world, and we want to make sure that we're protecting ourselves when we enter that environment. Personal protective equipment is really important. And we don't know what they're working with potentially. We may not be able to see it, smell it, feel it, right? But there could be materials in there that could contaminate our clothing. And so wearing the appropriate protective equipment, whether that means a lab coat, gloves, we always want to wear safety glasses, of course. There could be things that could be an explosion occurs or some flying or splashing or splattering that may get into your eyes. So eye protection is always a really important element of this. And then we have shoe covers and other things. So some of these protective equipment will be dependent on the type of laboratory and the requirements of the facility, but it's always a good idea to have an understanding of how best to protect yourself and don that protective equipment so we're minimizing our own risk. When we walk into a space, looking around that space and the type of activities that are going on, oftentimes, it's research. They're doing new stuff. We look in there, we may not understand exactly the type of hazards that we're seeing or the processes, but know that this is their work. They're doing this, and we don't want to mess around in there and move stuff and so forth, potentially contaminate their experiments or disrupt their activities. And so when we move our equipment into a laboratory to test a fume hood or to take measurements, we try to bring everything on our own cart so that we're not setting stuff down on the cabinets and so forth, trying to keep it all contained so that we have a better ability to move in and out of the space and basically do as little bit of impact as possible. When we're opening ceiling tiles or moving ladders around space, recognizing that the experimental equipment is very sensitive, it's very expensive. The last thing we want to do is drop a piece of equipment on a GC or a mass spec or some type of electron microscope or another piece of equipment that could be, tens of thousands or, $1 million in some cases for equipment. It's very expensive. And so we want to be sure that when we're taking ceiling tiles out, we're not dropping debris down on the equipment. So again, be aware of the environment, talk to the occupants, understand their needs, and we'll be better able to help them by optimizing the ventilation systems. So we're really here to talk about controlling exposure to hazardous airborne materials. And fume hoods are our primary line of defense. And so they're a ventilated device, but they're not a piece of furniture. They're not a simple piece of equipment. They're connected to a system, and we need to understand the holistic system in order to really understand how best to test and maintain the systems. So fume hoods can be used for a wide variety of hazards, and airborne hazards, as we know through the dealing with the COVID pandemic, airborne hazards are come in a variety of different types and sizes, and we need to understand the severity of that hazard as well as the quantity, how much material is being used to support generation, what is the generation potential of that material becoming airborne, what's the resultant concentration, and then what is the duration of exposure. When we look at people in laboratories, unfortunately, we've had to do some retrospective studies on where people have been exposed, and people have suffered everything from brain tumors to reproductive problems, respiratory issues, kidney damage, liver damage, all from their exposure in laboratories and improper either work practices or improper operation of the HVAC systems. And so we want to understand these hazards and the risk so that we can determine how best to mitigate that risk and provide a safe environment. So the dose is what causes the adverse health effect, and that's a function of the concentration times the duration of exposure. So if we can minimize the concentration and reduce the duration, we can reduce the dose and thus provide a safer environment. Now, everyone's pretty aware of what we've been through over the last year in terms of the COVID-19 pandemic, and its transmission has been a subject of some controversy. And I think as a general observation, we were too late in recognizing the aerosolized component as a significant route of transmission. So we can talk about the pathogens and aerosolized pathogens, and we're all familiar with, whether it's a droplet or it's a airborne material and so forth, but we don't really know the infectious dose associated with coronavirus. And in laboratories, they can work with all kinds of different materials, not just pathogens, but we might work with chemical hazards or radionuclides or some particulates or the combination of all those materials. So we have to be aware of the mechanisms of the source, the pathway, and the receptor. And how do we mitigate risk? By reducing the source, interrupting the pathway, and protecting the receptor. So we look into a laboratory and we realize that airflow patterns become very important. So we have maybe a sick person infected in the lab or in a healthy person in any space. And if we look at the airflow patterns within that space and the operation of the supply and the exhaust, in this particular example, we've got air supply that's mixing the air up in the space. So as a person starts to exhale, some of their effluent may come out as droplets, and that heavier material will have a tendency to settle, maybe on the floor and the surfaces surrounding that person. And generally, they recommend 6 feet to be outside of that general ballistic trajectory. However, if we have an aerosolized component, that starts to move with the air and it starts to spread within the space based on the internal airflow patterns. And so if we look at the effect of the internal airflow patterns, it begins to move those contaminants around the space till eventually the whole space is occupied. And so when we talk about a well-mixed environment, we're basically saying we're spreading contaminants throughout the entire space and everyone's getting exposed, albeit to a potentially lower concentration, but we don't know how low we need to go right now. When we don a mask, we expect it to restrict some of that effluent and that production of the ballistic trajectory of the droplets, but maybe there's some escape from the mask that will then move about in the lab. And so if you again look at the airflow patterns, maybe you're not downwind, but perhaps you don't know where the airflow patterns are. If we look at the airflow patterns, it's possible that it's actually moving it back towards the healthy people. So looking at not only the volume of airflow, but the airflow patterns are very important. Here's an example. We use a lot of mannequins in our testing to simulate people, and we're going to cover that in detail as we start talking about fume hoods. But we took our mannequins and we hooked them up to a smoke source, and then we can use this to show what happens as people exhale and what the airflow patterns are doing to the effluent migration. So we'll take a little bit of look here as our teacher in this particular case is standing at the podium, and we can see the materials migrating throughout the space. And so you can see the stratification, and that shows that it's not well mixed, that we're actually getting some movement of those materials. Let's look at another example. Here we have this mannequin is exhaling, and as we begin to see the production, the airflow patterns are moving that material back away from this person, but unfortunately, it's moving right toward this person, and now this person's going to get the majority of the exposure. And so if this was an infected person, we'd anticipate that we may have ourselves what we call a super spreader event, right? So we want to avoid this type of airflow motion in the space, and we can use the HVAC system, the supply diffusers, and the exhaust to provide more effective airflow patterns, and that's what we call ventilation effectiveness. So we're going to talk in detail about lab design and how we use the airflow within the lab to help reduce concentrations and support the performance of the fume hood. Another example, the importance of air supply and exhaust locations. On the example on the left, traditional room, the exhaust is above the door and the air supply is over the person, and a person's lying here on the bed, they're infected, and they're going to emit some potentially virus-laden particles. And on the right, we have moved the general exhaust to over the bed. And so let's take a look at the difference on airflow patterns. We're using computational fluid dynamics to show the trajectory of particles that are exhaled from our infected person. And on the one on the left, because of the airflow moving away across the bed to this exhaust location versus the one on the right, we can see on the left that trajectory is taking those particles throughout the entire space, ensuring that everyone's exposed and every surface is contaminated. Now we look at the one on the right. Just by locating the exhaust in a different place, we now get a much more effective control of that effluent, and we're minimizing the risk to the occupants. So this is an important concept around ventilation effectiveness and why airflow patterns matter. So our airflow systems, HVAC, is often overlooked, but they're extraordinarily important because they are installed to, number one, protect the occupants from exposure. Number two, to control the environmental conditions. And number three, to provide a comfortable workspace. We can't all go around with our own personal environment control system, so we have to utilize the building systems to provide these conditions. So looking into a laboratory, the objective of the HVAC system is to provide a safe and productive environment. And we're going to look first to capturing the hazards at the source. So that's where our fume hood comes in. We want to generate within the hood and remove those materials. But there may be materials that are generated inadvertently outside of a hood, and we're going to rely on the airflow in the room to dilute and remove those materials. So the two working together, the exhaust and the fume hoods and the general exhaust, plus the air supply should be coupled so that they're working in tandem to help dilute and remove the materials to provide a safe environment for the occupants. And the need for airflow is going to be a function of risk. But we also simultaneously have to provide good temperature control and good airflow conditions for humidity and so forth. So it becomes very complicated to achieve these objectives simultaneously. So we have to boil that down to what we call the demand for ventilation. How do we take these requirements and establish some operational specifications and some design requirements that enable us to design and effectively operate the systems to meet the needs? So first and foremost, we look at safety. What are the occupants doing? What type of hazards are they working with? How much flow is required for the fume hoods? What kind of airflow is required for dilution in terms of air changes per hour? And what is required for isolation and pressurization from the space? If there was a spill or some type of escape in the space, we don't want it to migrate to non-lab spaces, so pressurization becomes very important. We also have to simultaneously provide comfort conditions, so our temperature and humidity. And then, if we want to save energy, we want to modulate the systems based on occupancy and the use of the devices. So if they're not using a hood and they close the sash, we want the flow to go down. If they're not in the labs, we want to employ occupancy controls and reduce the flow. So overall, when we're looking at total flow, we want to find what is that minimum flow that's necessary to meet the needs of the occupants, and then that range of modulation that's required to get from minimum to maximum flow. And that definition is going to apply not only to the fume hood from sash closed to sash open, but also to the laboratory from minimum to maximum flow. So we need to know that minimum flow and the range of modulation. So let's build up a system. If we're operating a system, we first add some walls, and in that we're going to populate it with some hoods. So we've got some fume hoods and some local exhaust ventilation, but we've got to get those materials out of the building, so we're going to add some exhaust ducts and exhaust fans. So we have a single hood, single fan system, and we've got a manifolded system, multiple hoods connected to an arrangement of fans. But we've got to balance the flow. So let's put in some dampers. Now we've got dampers that can control and balance the airflow between the different devices. So we're exhausting air out of the space, removing the contaminants. But because we're pulling air out, we have to bring air back in to supply to make up air. And we have to control that distribution as well. So now we're starting to get pretty complicated. We've got an arrangement of systems that are essentially independent, the exhaust and supply, but they're not mutually exclusive. They need to work together in order to achieve the objectives of a safe and productive space. Now we can add some more complexity. Maybe we add some energy recovery to the controls, and maybe a building automation system with actuators and sensors and controllers that are detecting and modulating flow in response to these different operating modes. So now we're seeing a much more complicated system that is comprised of multiple components and subsystems. And we may add some sensing technology. Maybe we're looking at chemical sensing. And that's another layer of controls that we have to ensure is functioning properly and capable of protecting our occupants. So let's bring our occupants in, and now they start working in the hood, and we get our flow through the system, and we anticipate that all of these things are working properly and protecting the occupants. So if we then are modulating flow from minimum to some maximum flow, we expect to see the air handlers and the exhaust fans modulate that flow. They should be in balance. The exhaust flow should equal the supply flow. Now, oftentimes you want to run the building at a little bit positive pressure, so you're going to run a little bit more supply and exhaust. But as you open and close the fume hoods, that flow through the fume hood is going to modulate. That's a modern control. We also want the exhaust and the air supply to modulate in tandem so that they're providing a balanced system regardless of the operating mode, whether you're at low flow or high flow, they're in balance. And that means all of these parts and pieces have to work properly. Now, as the flow goes, so does the energy. Labs are very expensive. They consume a lot of energy, and the bulk of it is right in the HVAC system. So the more air that we condition and move through the building, the higher that energy consumption is likely to be. So we have some correlation between occupancy, operation, and energy consumption. So we want to find some metrics and make sure that we are monitoring this system to work properly over time. So as I mentioned, these systems are expensive. A typical lab building might be 100,000 square feet in size and cost you somewhere between $250 to $1,000 a square foot. That means a building is going to be somewhere between $25 million to $100 million. Larger buildings can be a lot more expensive than that. Some facilities have built buildings that have been hundreds of millions of dollars. Now, as it turns out, the HVAC is a very significant asset. It's about 15 to 30% of the construction for new modern buildings. So a tremendous amount of money is being spent on the HVAC system. Wouldn't it be nice to keep it working properly forever? From an operational standpoint, they're also very expensive. The energy consumed by the heating, ventilation, and air conditioning system can be anywhere from 45 to 85% of the facility's energy consumption. So when we look at all of the sources of energy consumption, HVAC is the greatest. You have lights, plug load, some other miscellaneous, but HVAC is going to be the bulk of it. And on average, it's about $7 per square foot per year. That's an annual cost for the 100,000 square foot building of about $700,000 a year. So tremendous amount of cost to buy the system, tremendous amount of cost to operate it. And what we have found through working with Lawrence Berkeley and an International Institute for Sustainable Labs and US EPA and others is that as much as 50% of that energy may be wasted by improper modulation of flow and inefficient systems. So we really need to think about how do we manage the airflow to minimize cost but meet the safety requirements of the occupants. Knowing how those occupants use the labs is really important. If we were to track the occupants and utilization of the labs over time, we may see that it's not always consistent. People like to say, oh, they work 24 hours a day in the lab. Well, that's not reality. We have a work week that's typically 2,080 hours a year. That's Monday through Friday, say 8 to 5, right? If you're working more than that, more than 40 hours a work week, well, maybe that time goes up, but there's 8,760 hours in a year. So when we look at the average amount of time people work, it's about 25% of the time. And when we actually look at the annualized occupancy of lab spaces, by and large, in most facilities, it's less than 25% of the time occupied. So that doesn't mean there's not exceptions. There certainly are plenty of exceptions. However, we need to understand this occupancy and utilization to better manage the space. So we're anticipating when we look at the system, we're going to see modulation and flow. Well, if we were to trend the airflow, would we see that modulation? If we looked at the operation over the, say, a course of a week, we start out on the weekends, it's at low flow, and over the course of the days, it starts to modulate. And as we get to the maximum, maybe that's a Wednesday at the middle of the day, we're at the maximum peak load, right? And then on the weekends, it goes back down to minimum flow. So now we have some understanding of this correlation between occupancy and operation. The question becomes, are these the right numbers? Do we have the right amount of flow through the building? And how would we know? So we can take a look at the operation of the systems, and I like to divide it into 3 zones. The first zone, what happens below the ceiling, right? Our hoods and our exposure control devices and our laboratories, that's what most of the users and the occupants see. And then there's the airflow controls where we find above the ceiling and the interstitials in the penthouses and so forth. Those are controlling the airflow. And then we have our mechanical systems that are in the penthouse, on the roof, and in the mechanical rooms. These systems all work together to achieve this objective. So we're going to look at this in 3 different sections. We're going to look at below the ceiling and above the ceiling in terms of how we test and manage and maintain the systems. So we'll start at the bottom first, and we're going to program from the bottom up. We're going to look at the hoods, then move to the lab environment, and then up to the systems. So starting at the hood is installed for the only purpose of protecting occupants. It is the primary safety device used in most laboratories to protect the occupants, and it's a fairly complicated device. It has a lot of different components that are necessary to provide protection. And so a typical hood is going to be about $1,000 to $1,500 a linear foot of hood width. So a 6-foot hood will cost you between $6,000 and $9,000 to purchase. But then you have to install it, which means ductwork and controls and fans and air supply. And that brings the cost up to $25,000 to $50,000 per hood, right? And then you add another operational cost on there of about $3,000 to $5,000 a year to operate that hood. It becomes a very expensive device for the sole purpose of protecting people. And so we want to make sure that it has the ability to contain materials, to capture those materials, and remove them from the hood in the building. And that's our job, and that's the purpose of this training course, is to make sure that they're effective in achieving this objective. So we're going to test it. We've got an ASHRAE 110 test that we're going to go through in detail today and tomorrow. We're going to talk about the operational conditions. How do we evaluate the conditions under which the hood's operating? So what's the face velocity? What's the cross drafts? What's the pressure? How well does it respond to open and closing sash? That's how well it's operating. But under that set of operating conditions, how well does it contain? We can visualize it with smoke. We can subject it to a tracer gas test. So VAV response and stability is also another test that we want to run. So we're going to try and protect people. We can do the containment test visually, or we can do a more quantitative tracer gas test. In that case, we're going to use a mannequin to simulate a person. We're generating a tracer gas inside the hood, pulling breathing zone samples and measuring them with the detector to see if anything escapes out of the hood. And so if the hood is functioning properly, it's protecting we're not seeing anything escaping out of the hood during this test, we have a high probability that it's going to work to protect the occupants. Now, at 3Flow, we've done tens of thousands of tests, and this is a result from about 40,000 tests on hoods throughout North America, and we see about a 15 to 30% failure rate of laboratory hoods. And that means that 1 out of 5 to 1 out of 3 hoods is not functioning appropriately or optimized to protect the occupants. And when we look at the factors that influence that performance, 20% of the time it's due to the design of the hood, improper aerodynamics. But 55% of the time it's associated with the operation of the ventilation system or the design of the laboratory. So these factors are really critical. We have to be able to identify them and remove them in order for the hood to work. And then we have 25% of the time it's due to work practices. So how is the hood being used? Do the occupants understand the capabilities and limitations of the hood? So Dr. Gerhard Knudsen was the inventor of the ASHRAE 110 method of testing. And he has told me, he said, Tom, we can idiot-proof these systems, but we may not be able to PhD-proof them, right? We have very interesting people doing interesting type of research, and we may not be able to predict exactly how they need to use the hood. And that's why it's very important that we understand their needs and then we test the hood accordingly. So we want to make sure that we've identified these risk factors and look how do we fix them. So OSHA comes in 1910.1450, the lab standard, says that it requires all facilities to ensure the proper functioning of fume hoods, and it requires proper testing and maintenance of fume hood systems. That's the law, right? So if you're governed by OSHA rules and regulations and have to comply with OSHA, it says that you must ensure the proper functioning of fume hoods. You must have validation that they're working properly and capable of protecting the occupants. And that's the only reason it was installed. So that's what we're going to do today and tomorrow, is talk about how do we achieve that objective. So you've already answered this question, and it came back about equal 100 feet per minute, and it depends. So let's look at this answer a little bit more detail. So what is the safe average face velocity? Well, when we look at velocity, that is the speed of the air entering the hood. So when we look at this different opportunities or different specifications, what we find out is that there is no velocity that is necessarily safe. We have not taken into account the occupant and the type of work that they're doing and the containment requirements. The velocity is just the speed of the air entering the hood. If you multiply that velocity times the area of the opening, that's the exhaust flow. So the velocity times the area. If you have 100 feet per minute velocity and you have a 10 square feet opening, say 5 feet wide, 2 feet tall, 10 square feet, that's 1,000 CFM of exhaust. That doesn't say anything about containment. It doesn't talk about the degree of protection provided. It's just a velocity. And we have to think about other factors that could influence the containment capability. For example, what is this hood missing? All right? If we know the components of the hood, we would identify that it's missing an airfoil sill, very important element to the capability of the hood to contain. Doesn't matter what the face velocity is if it's missing a vital component. We take a look at another hood. Clearly you see the missing airfoil sill, but what other factors do we have here? Well, we find out that, well, the hood's made out of wood, for one. It's rectangular in its shape. It doesn't have any aerodynamic entries, and it's right next to a door and a traffic aisle. So people walking by the hood could create a cross draft and pull materials out of the hood. So these are factors that could influence the containment. We have other hoods. This hood itself, if it's manufactured out of a cardboard with duct tape and some flex hose, I'm not saying it's inappropriate, but I am saying it may be questionable as to whether it's providing the degree of protection required. So we need to have properly engineered devices because safety is number one. Another example is we're looking at a hood. We got called in to test this hood because people were using this hood with some ether and they could smell the ether and they were saying something's not right. So I got called to come in and take a look at this hood. And as we were testing it, sure enough, it failed the tracer gas test. And so we could detect it in the space. And when I got on the ladder and I looked above, I said, oh boy, it's got an exhaust fan right above the hood and it's blowing the air down the duct. But then I looked on the duct and I noticed that something had been written on it. And when I looked at it, it said leaks in this area. So I automatically said, well, here's the problem. It leaks in this area. So we were able to detect that. In this case, the positively pressurized duct downstream was not adequate to provide containment and removal of the materials. And so we were getting some escape. Now, another type of hood system, this is equipped with a variable air volume system. When you close the sash, it reduces the flow. But they were working with acids and they were generating large quantities of material. And as they were going out of the ductwork system, that minimum flow wasn't sufficient to remove it from the hood, and it rained back into the hood. And you could see it dripping down the back of the panels inside the hood. So that indicates that it's just not sufficient to provide containment and removal of the materials from the hood. So we have to look at the right flow. Another case is you walk into a laboratory and there's all kinds of activity and you go up to the hood and you see something like on the left or the right. You can't even get in the hood, right? And there's a sign here that says, please keep clean. Well, apparently they missed the sign because it's so loaded up with stuff you can't use the hood. And if we look at the hood on the right, it's got so much stuff in here you can't close the sashes. So the question is, can you really test these hoods? Can you verify they're functioning properly? And the answer is no, you can't, right? Despite there being a sticker on the hood, it's inappropriate. We can't test these hoods because they're not going to function the way they're expected to in order to protect people. In addition, fume hoods are very expensive. We've already talked about their cost to install and operate, and then we have them being used for other purposes. Now, it's a pretty fancy storage cabinet, right? But it's also a very expensive storage cabinet. This hood right here, because it's 5 feet wide, maybe 6 feet tall, that's 30 square feet. Multiply that by 100 CFM, you've got 3,000 CFM of air. Multiply that by $5 per CFM year, and you're talking a lot of money, 15 grand a year in operational cost for a storage cabinet. All right. And then we look at how are the hoods being used, right? If we have 100 feet per minute and the hood user's putting their head inside the hood, we're not going to be safe, right? No amount of face velocity is going to protect people from exposure if they're working beyond the plane of the sash and exposing themselves directly to the work. It's just not capable of maintaining containment and protecting people under this set of operating conditions. So all of these factors are really important. Another factor that we're going to look at is the supply. So we have our hood here, our supply diffusers in the ceiling. Now you may look at that and say, well, that looks okay. But what if we looked at the distance of the diffusers from the opening and said that cross drafts are really important? If the ceiling tiles are 2 feet by 2 feet, then we know that this diffuser is 1 foot, 2 feet away, so 3 feet to the diffuser. And when we look at the airflow patterns of discharge, are blowing right at this opening, and that diffuser is too close. All right, so we're going to go through all of these factors in more detail, but I'm just showing some examples now. Now here on the roof, we expect the system, the hood, the contaminants to go out of the hood, through the ductwork, and be discharged out of the building in a safe manner. What's wrong with this picture? When we look at this ductwork, we have our person working on the roof. We've got an air supply intake here. Well, we look at it's coming out. It's a square duct going into here. It's not going to be very efficient. The stack height's too low. And when the discharge coming out, it's going to go downstream right back into the air intakes. Re-entrainment, very significant problem. It's something that we need to test for and make sure that these problems are eliminated. So many factors can influence the containment capability of the hood. We have the work practices, we have the design and operation of the hood, we have the lab design, we have the airflow controls from minimum to maximum, we have the exhaust discharge, and the re-entrainment potential of bringing air back into the building that's contaminated. So when we're looking at hood testing, we need to evaluate all of these factors to make sure that we're achieving our objectives. So fortunately, we don't have to reinvent the wheel. A lot of this information's already been produced and it's available in different standards and guidelines. So let's take a look at some of these examples. So we want to specify the appropriate measures and specifications, and we're going to start with the right type of exposure control device, then talk about monitors and controls, then the lab design itself, the operation of the ventilation system, and whether it's being tested and evaluated properly to make sure it is, in fact, meeting the requirements for safety and efficiency. So these are all covered in various different guidelines and standards. I've had an opportunity to work with these different organizations, and they come from different perspectives. We have ASHRAE, it's the American Society of Heating, Refrigeration, and Air Conditioning Engineers. They have a method of testing. That's what we're talking about here. They've got a lab design guide. They've got a classification of lab ventilation design levels. We'll talk about that in more detail. Then we have CIFA. That's a Scientific Equipment and Furniture Association. That's a group that is mainly comprised of the fume hood manufacturers. And so they have put out guides on how to select different types of hoods, how to operate those hoods. And so that's guidance directly from the manufacturers. The American Industrial Hygiene Association is putting out standards for proper operation of the systems from a safety perspective. So the ANSI Z9.5 is their standard, and I'll talk more about that in a moment. And then there's other standards that are available through the Public Works and Government Services of Canada. Great guides in terms of providing information. So my point is here, these should be in your library of available information, and we'll make them available, those that are public domain, so that you can download these documents. And finally, we're also working in conjunction with the American Industrial Hygiene Association to develop a lab risk assessment. We'll talk more about that tomorrow afternoon. So let's get back to fume hood testing. The methods of testing performance of fume hoods is where we are concentrating our efforts. There are some other companion guides that can be complement the guide, the ASHRAE 110. The EPA performance test methods are a very extensive guide to testing and has lots of forms. We're going to talk more about how we utilize this information in our testing program. So another poll here. Whip up this poll. We've got 2 questions on this next poll. All right, let's launch this poll. And the questions are, have you witnessed or conducted an ASHRAE 110 fume hood tracer test? And the second question is, have you ever measured room differential pressure? All right, so we're going to look at the responses here. We're getting pretty good response. Seems people are still paying attention, which is a good thing. Okay, we're coming up on about 80% response here. We'll give it just another minute. Okay, here we go. So I'm going to end the poll, and then I will share the results. And the results indicate that about 30% of the participants have actually witnessed or conducted a 110 test, but about 65% have not. So we've got a lot of things to cover here. And as far as measuring room differential pressure, again, we have about 35% that say yes, they've done that. And then there's a majority of people that have not. So we're going to cover these methods in more detail. All right, so we'll get back to the slides. Gary, are we back on the slides? Okay, perfect. All right, so the ASHRAE 110 test was written originally in 1985. It was updated in 1995, and then most recently again in 2016, and it's currently under revision right now. And so it covers a variety of different methods, from measuring face velocity to conducting smoke visualization tests and conducting the tracer gas test. And we're going to go through this standard in more detail, but first we need to look at how is it employed. So we measure the conditions under which the hood is operating. So first and foremost, we're going to look at the hood and the lab and make sure it's properly installed. And then we're going to measure face velocity with a face velocity probe. We're going to measure the cross drafts in the lab, and then evaluate how does the VAV system modulate flow, the variable air volume system. If a hood is so equipped, we anticipate it's going to modulate flow in response to sash movement or occupancy, and we want to make sure that it does in fact modulate flow effectively. Under that set of operating conditions, we're going to look at airflow visualization. What are the airflow patterns within the hood, and how well does it dilute and remove materials? And then subject it to the tracer gas containment test. Now these tests can be specified 3 ways. As manufactured, that's before you purchase the hood. You want to know everything you want to know about that hood and to design the system properly. So you test it, determine the performance envelope, and now you're ready to install it. After it's installed and before it gets used for hazardous materials, we want to look at the commissioning of that hood and the impact of the hood design and the lab environment on its operation. And then finally, the as-use test is after they set up their experimental apparatus. What is the impact of the experimental apparatus on containment? The last test, the as-used, is really at the discretion of EH&S. If there is a sense that the apparatus and the process or procedures are going to influence containment, then it may be necessary to specify an as-used test. The EPA, U.S. Environmental Protection Agency, has a fume hood standard, and it has information on design specifications, methods to inspect and test the hood. It has recommended performance criteria, and there are forms. And guess what? It's free. It's public domain, and all of this is available. We're going to be covering this in more detail because it's probably the most comprehensive expansion of ASHRAE 110 in terms of the tools that you can use to properly evaluate hoods. When looking at the criteria for performance and for ventilation systems, the standard of care is the AIHA Z95 American National Standard for Lab Ventilation. That document is also under review, and now it's for the American Society of Safety Professionals, which is the ASSP, which was the ASSE. But that is providing the guidelines for operation and design and operation of laboratory ventilation systems. And it requires that all facilities have a hazard and risk assessment, a lab ventilation management plan, and that they're conducting ASHRAE 110 hood tests. So this standard sets the basis for the criteria for determining whether hoods function properly. When we look at detail into this document, even though it's under revision, we're going to keep the general chapters. And I'm not going to go through it more in significant detail, but you can get this document, and it has the guidelines for the ventilation management program, for the different fume hoods and other exposure control devices, how to design and operate the ventilation system, how to commission and conduct routine tests, and some guidelines for maintenance and ongoing evaluation. So this is the ANSI Z9.5 American National Standard for Lab Ventilation. I mentioned the CIFA document. The CIFA document is a document that helps to define the types of laboratory fume hoods. There's many different types and sizes. So this CIFA document, published by the manufacturers, talks about the different components, the types of testing, the influence of the environment, and what some recommended work practices to make sure that hoods function properly. They've also expanded into the other types of exposure control devices. So it's not just fume hoods, but you may have biosafety cabinets or local exhaust snorkel hoods. You may have canopies and other types of devices that are used in the space that require ventilation. And so this CIFA document helps to define the different types of hoods. There's many different types of chemical fume hoods, from benchtop bypass hoods to floor-mounted hoods. And so these different types of hoods may have different application, and they're not to be confused with a biosafety cabinet, which is more about use of biological materials. And so by looking at this document, it helps to define what are the hazards, the type of quantities, and the generation rates, and what is the hood for, so that you can more define the type of hood and what our expectations are for proper operation. And that same too applies to, say, ventilated safety enclosures, which might be balance enclosures or glove boxes or other types of spot exhaust, necropsy workstations, and downdraft hoods. These all have different applications. And so this document helps to differentiate the different hoods and provide some guidance on when they should be used and how they should be operated. There's some matrices in here that tell us about the hazards quantity and the rate of generation and what types of materials that they're appropriate for. And we can also look at the same for all the different types of devices. So again, it's a good reference. It's something that's helpful. You should have it in your library, and you can download it right from the CIFA site, but I think we've made it available here. Another important document that's been published recently is the ASHRAE classification of lab ventilation design levels. And I like this document because it creates a perspective on how to evaluate labs and hoods based on their level of risk and their protective capability. So as we look at this ventilation system, I've lost audio. Oh, we're back? Okay. As we look at this system, this is the same one we covered before, comprised of all these different components and parts and pieces. And so how do we go about investigating whether it's designed and operating properly? And it would be nice if we knew a little bit about the degree of protection that these systems afford. So the lab ventilation design level says that there are 5 levels. Level 0 is the lowest level of protection. Level 4 is the highest level of protection. So if you look at the level of risk, if they're working with low to no hazards, they don't require a lot of protection. But if they're working with chemical warfare agents, they're going to require the highest level of protection. So we want to make sure that the hoods are appropriate and the ventilation systems are appropriate to provide the required level of protective capability. And we call that the lab ventilation design level. So let's say that we go into a laboratory and we look at the associated risk based on the application from negligible to extreme. and we want to match that to the protective capability of the space. If the risk level is very high, but the protective capability is low, that's a big difference, and that would be bad, right? We want to have the protective capability greater than the level of risk, so that when we look at that difference, that is the margin of safety, or it's also an opportunity. So if the protective capability greatly exceeds the level of risk, maybe we can right size that system and save some energy, right? So, but we need to know the risk and the protective capability required in order to ensure that we're making the appropriate change. So as that risk level increases, so does the requirements for the hoods. You can start with a canopy providing low to no containment and low to no protection, a snorkel a little bit more, followed by a ventilated enclosure or a fume hood. If a fume hood's not good enough, maybe you need to go to a glove box or some kind of special isolator. And the same thing can be said for the laboratory. As we increase the level of ventilation and ventilation effectiveness, we can begin matching the exposure level. So knowing the risk and knowing the protective capability, we can match these to make sure that they're safe. And we're going to test the fume hood to make sure that it provides an adequate level of protection. So looking into the laboratory again, the protective capability should always exceed the demand for ventilation. And if we do that properly, we're going to mitigate the risk. And we want to start with the laboratory and look at what's in that laboratory. What are the hoods? What's the general exhaust? What kind of air supply? How are they working together to provide a safe environment? And what are the minimum and maximum flows? Someone has to program this. And when we test it, somebody has to tell us, what is it we're doing? What are we looking for in terms of safety? So we're going to look at all of these different evaluations during the testing, but we're going to start with the hood. The hood is where we start first, and we're going to look at the sash opening configuration, the maximum exhaust of face velocity multiplied by the opening area, and then what happens when we close the sash. How important it is to have the right minimum flow when the sash is closed. So, as I mentioned, hoods come in all kinds of different shapes, sizes, and types. So we have benchtop hoods versus floor-mounted hoods. This happens to be a horizontal sliding sash. The panels move left to right. But we have vertical sliding sashes that go up and down. This is an auxiliary air hood. It brings air in from outside and distributes down the face. And then over here we have a benchtop hood, but it's got dual vertical sashes. So both sashes can open independently. So we need to know the difference in these types of hoods and their design conditions so that we can properly test and evaluate the hood. We look into the hood and at the hood to determine whether it has the appropriate components. As I mentioned earlier in a slide, the airfoil sill is very important. It fits over the work surface and helps to streamline flow into the hood. Then at the back of the hood, we have the baffles. And the baffles have slots for controlling the airflow distribution within that hood. Our vertical sliding sash moves up and down. And so you can open and close the sash to restrict the opening, or it may have horizontal panels that move left to right. So vertical goes up and down, horizontal panels move left to right. We may have some type of velocity sensor and a hood monitor telling the users how the hood's operating. A bypass, when you pull the sash down, it may open up a gap here at the top, allowing flow into the hood. Behind the baffle is the outlet duct and collar, and then some type of controller that's modulating the flow. If it's variable air volume, if it's constant volume, it's fixed. And so the flow through the hood would be constant in a constant volume hood and variable in a variable air volume hood. Probably kind of self-explanatory. When we look at a hood from the top view, the manufacturers build these hoods and they are somewhat like furniture. They're traditional size, stock sizes, but the airflow patterns are more complicated than just straight streamlines. If we look at it from the side, we get vortices that form in the top portion of the hood, and that has a rolling vortex, and then that airflow may split as it moves through the slots into the plenum and then out of the hood. When a person stands in front of the hood, it becomes more complicated because of their position of the sash. In this case, it's a vertical rising sash. We have the user standing in front of the hood, and you can see he's looking through the glass into the hood to work in the hood at some sash height restriction. But it makes it difficult to access the top interior of the hood, whereas a horizontal sliding sash hood limits your side-to-side access but gives you the ability to access the top interior of the hood. So both of these have value, but they can be limiting as well. So the vertical sash allows left to right movement but limits your vertical, and the horizontal panels limit your left to right movement but access the vertical. So these two designs are going to require different types of tests to evaluate. We need to look at what are the operational specifications. If we have our hood operating and our air supply, we need to know what is the flow. And that's going to be a function of the face velocity when the sash is open. So we need to know the configuration of the sash. Is it going to be used 100% full open or at some restricted opening height like 18 inches? We need to then determine the average face velocity. 100 feet per minute is traditional, but a high performance hood could operate at 60 feet per minute. And then is the flow going to be constant regardless of sash position, 24 hours a day, 7 days a week, or is it variable air volume, which means it may modulate flow depending on its operating mode, occupied, unoccupied, sash open, sash closed, and how low can we go when the sash is closed. We may still have processes and procedures in the hood. Looking at the top view, as airflow recirculates around the body, it creates a vortex downstream, and that vortex then can pull materials back towards the body. So a person standing in front of the hood can create an obstruction in the path of airflow, allowing for some escape. Let's take a look at a video here. So here we're generating smoke in the hood. There's no one standing at the hood. You can see it's containing properly. And all of a sudden we push our mannequin up to the hood and we see that it begins to disrupt the airflow patterns and we get some escape, right? So it was containing properly without a person standing in front of it, but the moment we put an obstruction in front, it begins to create those vortex eddies and escape from the hood occurs. And so when we move it away, you can see it draw out of the hood. And so movement near the opening is also very important. So we've demonstrated that a person standing in front of the hood can have a significant impact on hood containment. All right, I won't make you watch that again. All right, so now you can also affect airflow patterns based on location of obstructions. If they're directly downstream of the body, they're going to create more impact on containment than if they're on the sides. We want to have the space between the body and the slot open to the degree of potential, and that's why we generate downstream of the body during tracer tests. We also want to look at the movement of the sash. When the sash is in the closed position, we get flow through the airfoil and through the bypass into the hood, and this vortex forms to accumulate materials inside that hood. When you open that sash, that high concentration can escape out and expose the occupant and then be recaptured. So that response time and the aerodynamics inside the hood are very important to minimize that potential for escape. And that's why we say open the sash slowly to allow for this system to recover and capture materials, and that's why we're going to test it in what's called the sash movement effect test. I've mentioned the bypass now a couple of times. The bypass is when you close this sash, it opens the area above the sash to allow flow into the hood to help dilute the materials in the top portion of the hood. On a variable air volume hood, this is a restricted bypass. They make it smaller. And now, when you pull that sash down, a smaller amount of air is moving through the top of the hood. If we go too low a flow, it's not going to provide adequate containment, and we're not going to dilute and remove the materials appropriately. So the bypass position is very important. It's bigger on constant volume hoods than it is on variable volume. Now, we've looked a little bit at the hoods. Let's look at the lab design. You can see from this picture right here, it looks pretty clean, but I notice right above the hoods, I've got my supply diffusers blowing right at the hoods. I'm anticipating a problem. So looking at the hood, we talked about the min-max flow for the hood, but we also have to match it to the supply in the lab. So what is the balance how much flow is going out of the hood, how much air supply is coming in, and what is the isolation or pressurization required to provide the appropriate pressurization for the space, and how much flow is required for temperature control. So the thermostat responding to the general exhaust, modulating to provide the right supply. And so all of these things are working together. We can't have one independent of the other because they all influence the air balance. And then what's the magnitude of the airflow from an air change per hour perspective? So these are all factors that need to be taken into account, and we're going to go through the measurement techniques to evaluate. Looking into a laboratory again, we see a couple of issues here. This hood is located right on a traffic aisle near a door, so that's going to cause some issues. The supply diffusers are blowing directly at the hood, so that could be cause of cross drafts. And the thermostat's located way over here, so by the time the temperature changes, it may be going through cycles of cold to hot, cold to hot. And because of this door being close to the hood, we had to put an interlock on it so that people couldn't go in or out that door when the sash was open. They had to use the secondary egress route. So that led us to some identification of some recommendations for hood location. We want them to be at least 5 feet away from a supply diffuser. We want hoods to be 4 feet from traffic aisles. We want to be at least 3 feet away from major obstructions like refrigerators or freezers. And 2 hoods facing one another should have the distance, the width of the hood should be the distance between them. So if you have a 5-foot hood, it should have 5 feet between them. If you have 6-foot hoods, it should be 6 feet. And that has to do with the hoods stealing air from one another. So if they're too close, they'll compete for airflow and can be a problem. The location of the air supply in the room is really important. So in this hood, you see the line of hoods. We have our air supply diffusers over the benchtop. Now they're close because they're only a couple of feet away. And when this was blowing cold air, it was dumping. But when it was hot air, it was blowing across the ceiling, and that was causing turbulence in front of the hood. So we recommend the diffuser should be at least 5 feet away from the hood. So if you drew a diagram here, you'd say the no diffuser zone is 5 feet around that hood. There should be no diffusers in that zone. It doesn't mean it can't work with a diffuser in that zone. It just says it might be an issue. And there are so many different types of diffusers that we have to look at the projection and the throw of velocities from these diffusers and how it might impact the room airflow patterns and the performance of the hood. And we have a test called the cross drafts to evaluate it. So why wait till testing though? If we get the drawings, why not look at the drawings right away and say, do we have a problem? So many of you may have seen drawings like this. Unfortunately, when we see a drawing like this, it's so detailed that it's hard for us to determine what we're looking at. So let's blow this up a little bit. Now we blow it up and we can identify here's a fume hood, here's a fume hood at the top, and then we have supply diffusers. And let's color code those so that we know what we're looking at. Our fume hood, supply, and we immediately start to look and say the supplies are too close to the hoods. Why install them now? Move them so they're not going to be a problem, so we eliminate that before it becomes an issue in the lab. In this example, and we're going to show the results of this over the next day and a half, looking at a supply diffuser. It's too close to the hood. It's only 3 feet away. It's got an airflow velocity that's directly impacting on the plane of the sash. And then we had to blank it off. We had to put tape over it to see if we could improve the performance of the hood by creating a different airflow pattern. And I'll show you the results as we move forward through the different test discussions. We also have the room pressurization. When we're working in a space, it's nice to know if that room's under negative or positive pressure, because how can you test a fume hood if the room's not operating properly? So in this room over here, it's under positive pressure. It's blowing air out of that space. But this room is under negative to this room and the corridor. So it'd be nice to have just a little bit of an airflow direction line to tell us where those airflow patterns should be coming from. Now, we also have the circumstance where we're looking at this pressurization. So we've got an airflow direction on there, but we may not have the right magnitude of the pressurization. So we want to look at what is the pressurization for the space. So our supply diffuser and our exhaust, we take a look at this value, and if we have some type of pressure gauge, and pressurization is important, right? If I go back just for a moment to this diagram, we're looking at this diagram and we're saying the reason that we have pressurization is important is because if there's a spill or there's an escape from the hood or there's some other type of leak, we don't want that material to be migrating to non-lab spaces. So the air balance is set up to provide a flow cascade from areas of lower hazard to higher hazard, and that the airflow is in the appropriate direction. And if that is true, we need to know the magnitude of that airflow so that we can determine whether it's improperly balanced. So again, we look at our side view of the lab space, and we have some type of pressurization or a gauge maybe, and then we're looking at the total exhaust and the total supply. If the exhaust, the total exhaust from the space exceeds the supply, then that means that the offset flow, the exhaust minus the supply equals the offset. That's the airflow coming in from non-lab spaces into the room is being drawn into the room. We're exhausting more air out than is being supplied, so it's sucking air into the room through all openings. Typically underneath the door or around the door is going to be one of those air inlet spaces. And so when we look at this, we're saying that the exhaust exceeds supply, so this room is under negative pressure. Conversely, we may have a space that's operating under positive pressure. If the supply exceeds the exhaust, then we have more supply coming into the space than is being exhausted, and that means that that excess air is going somewhere and it's going back out of the space. So in this case, the exhaust minus the supply equals a positive, meaning it's going out of the space, and so this room is under positive pressure. Now you can imagine that if you had a spill in this space or there was an escape from a hood, it's going to exfiltrate from this space into the corridors, and people begin to say, oh, I'm smelling odors. Where's it coming from? You need to look at the pressurization. So the pressurization of the space and this concept of the volumetric transfer error, the offset transfer, is the difference between supply and exhaust, and it must be appropriate in order for the hood to function properly as well. So this is often overlooked when we're evaluating the air balance for spaces. Okay, so this was the question, have you ever measured room differential pressure? And quite a few people had, but quite a few people didn't. And so we're going to talk about how to do this measurement and what is the appropriate technique. In addition, we need to look at what are the types of monitors that are available. I think that every room that should have a monitor to indicate this pressurization, and there's different types. There's the ping pong ball that's in a tube. It's kind of neat. If it's under negative pressure, you'll see it on this side of the wall. If it's under positive pressure, it'll blow it to the other side of the tube. Wish I invented that, but I didn't. I'd certainly probably be retired now if I had. The magnehelic gauge is another very inexpensive gauge that you can measure the differential pressure. It's a sight type of gauge. And then you have your electronic gauges that are based on pressurization. This gauge needs to be calibrated and then reflect the actual pressure. And now you can use that in the monitoring and maintenance of the systems. So having an ability to manage the airflow, looking at the hoods, the laboratory environment, and the pressurization, all really critical to making sure that the hood is functioning, the lab and the hoods are functioning properly. And so all of these conditions are important. Okay, so we're a little bit ahead of schedule. We're going to take a 10-minute break, And we'll come back after the break, and we're going to start in on hood testing procedures and evaluating the operation of a hood. Okay, thanks, and we'll take a break. If you have any questions, please put them into the question section, and we'll see you back here at 2:40. 2:40. Okay, welcome back, everyone. Hope you enjoyed the break. You loaded up on some caffeine. So we're ready to go for our next section here. So we've covered the introductory materials. It's really important that as we are talking about the testing methods, that we have some background on the hoods, the lab, and the systems, and how important all of these elements are. And that provides context for this section, which is the testing methods. And so today, in this session, we're going to cover the hood operational tests. And then tomorrow, we're going to look at how does the hood perform under that set of operating conditions. So we're going to do two things in this next section. We're going to talk about the hood test methods, and then we're going to go over to the hood, and we're going to run a few examples and then show some methods of testing, some actual measurements. Okay. So testing fume hood operation. We are equipped with the appropriate safety measures, our protective equipment. We go into the lab space. We're going to review the hood and make sure that the lab environment is appropriate and go through a series of tests. As we mentioned previously, there are three methods of measuring, of specifying the ASHRAE 110. As manufactured, that means that we're testing the hood by itself. How does the hood perform as a function of its design, right? And then we'd like to know, where is its failure point? How low can we go on the flow before it begins to fail? So we're going to apply a series of tests. We're going to do our operational test. That's going to inspect the hood in the lab, make sure it's all properly installed and it's equipped appropriately. We're then going to conduct face velocity tests, measure cross drafts, and do a VAV response and stability test. And then, under that set of conditions, we move to the performance tests. Now, once we understand that the hood is properly designed, the as-installed tests are about putting the hood in the lab, installing it, and then operating the lab as it would be when the users occupied the space. We want the hood to be in move-in ready when we do the as-installed, the commissioning test. Oftentimes, during construction projects, it'll get ahead of the full commissioning of the lab space or the full air balance of the systems. Just because the hood is installed doesn't mean it's ready to be tested. Just because it has exhaust flow, these other factors could influence the containment. The conditions in the lab, the total flow, the pressurization, these are all important elements that can influence the containment of the hood. So the as-installed commissioning test should be the very last thing that's done to certify the hood after the labs have been tested and balanced and they've been commissioned, saying all the parts and pieces are working properly, it's working as we expected. The last thing to do is to certify the hood and say it is now functioning, it's ready for use, and we want to do that before people subject their health and safety to working with hazardous materials. We want to have an assurance that it's going to function properly. And then finally, there's the as-used test. So under the as-used test, we're going to apply the same level of tests as before, except now we're trying to evaluate the impact of operational conditions, how the hood's being used, the influence of the operator in some cases, as well as the experimental apparatus in the hood. Now that's really up to the discretion of the EH&S, because a lot of times we know the hood's functioning properly, is providing a good degree of containment. If it's used within the capabilities and limitations of the hoods, it should provide adequate protection, but sometimes we want to know where it's on the edge. So we have a process. This process starts with a inspection. We want to inspect the lab hood, we want to inspect the lab environment and the system. And then we move from there to verifying that all of our equipment is properly calibrated and functioning, our test equipment. Then we want to conduct our hood tests. So we need to evaluate the hood itself and determine what is the appropriate sash configuration, what are the baffle settings, and how other set points are manipulated so that we're testing it under a defined set of conditions. Then first thing is measuring the cross drafts. If the cross drafts are too high, if we've got air blowing on the hood, that's going to affect the face velocity. So we want to eliminate that variable first. Then our face velocity test, and if it's appropriately balanced with the right flow, then we want to make sure that the VAV system is modulating flow properly. Those are our operational tests. Following the operational tests, then we can move to the performance tests, which are the airflow visualization and tracer gas containment. Today, we're going to be talking about the operational tests, and tomorrow we'll come back and look at how does it perform under that set of operating conditions. So you can look at these tests in terms of how they're applied. From the as manufactured tests, we want to do all of them plus. We want to do the inspections, the operational tests, and we want to challenge it not only under the static tests with a fixed sash, but how does it work if there's special tests, dynamic conditions? What are the weaknesses of the hood and where is it going to fail? That's the as manufactured test. The as installed test, we're finding it after it's been installed and the proper tab and testing, adjusting, and balancing has been completed and all the parts and pieces have been commissioned. Then we're going to apply the test to set the baseline or the benchmark for the future operational test. And then on an as ongoing basis, the routine maintenance tests are the inspections plus our flow measurements, velocity, and dynamic response. And then we only have to do a smoke test, right? If all these other conditions are operating properly, if the hood's operating the same as it did during as installed, we'd expect it to give the same level of performance. But if it's beginning to modulate or any of these conditions have changed, then it may need to be recommissioned again to make sure that it's back to the correct operational state. So your routine tests are a simplified measurement, but they're not just face velocity. We have more tests to conduct, and I'll show you why as we move forward. So our sequence: inspect the hood in the lab, do the lab environment tests, measure the cross drafts, then the face velocity, and finally our VAV response and stability test. And those will help us identify and eliminate variables as we move through the testing process. So let's start first with our hood inspection and our lab inspection. So looking at the hood, we've talked about these various different components. We have the work surface and the airfoil sill. Is it properly installed? We have the sash. Is it go up and down? Does the sash move left to right? This is a vertical sliding sash, and so it has to function properly. So we'd raise it and lower it. Does it move with less than 5 pounds of force? Opening and closing that sash. Then we have the baffles in the back of the hood. The baffles are aligned to help remove the contaminants from inside the hood. If they're not properly installed, they're not going to function right, and we're going to get issues with performance. And then we have these access panels. The access panels provide access to the plumbing and other features that might be in the sidewall of the hood. And so if we're missing this access panel, then it's going to be leaking air into the hood and it's not going to perform properly. So again, access panels are a very important feature of the hood, and they're also can be quite challenging to get back in. And I think that that's probably should be an interview question in the future for my employees to be able to say, okay, your first task is to get this panel back in the hood, because they can be a real challenge, I can assure you. And then we look at the monitor. Is the monitor properly installed? Is it energized, and is it reporting a velocity or flow or pressure? And is it functioning properly? Now, if all these features are right, then the hood should be ready to test. Now, we can observe on this hood that the distance between the airfoil on the left and the airfoil on the right, it's not aligned properly. This hood's not properly installed. It's kind of arranged so that it's pushed too far back on the left, and so that may impact its operation. So now we've looked at the hood and we said, okay, it's properly installed, it's ready to go. We understand its current operating conditions. Now let's look at the lab environment. What factors are influencing the containment capabilities of the hood, and is the lab conducive to the proper operation of the hood. So we want to do some lab environment tests. First and foremost, oftentimes we look at the reporting of flow by the building automation system. What information is being reported about the operational conditions of that space? And it may report the exhaust flow and the supply flow and the other conditions, maybe pressurization is a factor. Well, are they right? Who knows, right? So oftentimes we find errors between the reported value and the measured value. And our measurements are what's oftentimes used to calibrate and confirm the accuracy and precision of the controls. So their reporting is only as good as our measurements. And so our integrity is closely related to the accuracy and precision of our measurements. So if we're not accurate and precise, we're going to be giving improper information upon which to confirm the calibration or to verify the proper operation. Now, we want to measure room temperature and pressure. If you've got a variable component in this system, you've got different operating modes, we want to measure it with sash closed and sash open, right? That flow through the room, if it's negatively pressurized, should be the same whether it's sash open or closed, because we still want to maintain secondary containment. So making sure that it has the right pressurization from across that door, across the operating mode, sash closed, sash open, confirm it across the range, and then confirm that the monitor and sensors are reporting correctly. Now, in this particular case, the room pressure measurement, let me go back just 1 second here. It's quite easy to do. We take a meter, we put it across the door. We're going to show you the technique later, but essentially it's a very simple, easy measurement. It only takes about a minute to measure this pressurization, change the operating conditions, and measure it again. So this shows the results of 2 buildings of pressure measurements on the lab space. It was designed to be under negative pressure. We expect it to be under negative pressure for safety. We go in, we find 30% of the spaces in this building are out of pressurization. So that immediately says to us that it's not properly balanced. The secondary containment of the space is being jeopardized, and so we need to ensure that it's properly pressurized. And then this space down here wasn't so much a matter of incorrect pressurization, it was excessive pressurization. In that case, you can see the doors are hard to open or close. The airflow coming into the space is very high, causing high cross drafts when we have excessive negative pressurization. It could be a safety issue if the doors are slamming shut. It can be a safety issue if the cross drafts produced by this pressurization is creating turbulence at the hood. So the fume hood should not really be tested until it's confirmed that the pressurization of the space is correct. If you test the hood now and the space is not correct, you're saying, yes, it may or may not be working under this set of prevailing conditions, but if those prevailing conditions are incorrect or improper, then you may be giving a false sense of safety. So it's important that the lab and the hood are operating properly in order for you to put that sticker on the hood saying it's certified. Now I show the EPA hood inspection sheet here because there's no reason to recreate it. All of the information is right here in its public domain. So as one of my mentors said, plagiarize, that's why God gave you eyes. He also said, make sure you reference and give credit where due. In this case, the EPA has done the work. Let's use some of their forms and gain from their prior knowledge. And so we can go through, there's the inspection, go through and click the right boxes, enter your dimensions, enter the sash information, record the information about the baffles, and there's other information about the monitors and so forth. It's all right there. They also give you a form to record the information about the lab environment, the space dimensions, the airflow conditions, the differential pressure when the sash is open and closed, and it gives you a space to put in a sketch. We think it's important to sketch the space because things can change. And so the data that you collect is only as of that time and date tested. If they put a new wall in or move a diffuser or put a new piece of equipment, that could influence the test results. So we want to have the conditions recorded under which we conducted the test so that we have a record of the performance at that time, and that sets the benchmark for the operation at that moment in time. We'll also take a look at the equipment that we're using. What is the instrumentation that's being used to conduct the test? Record the manufacturer, the serial number, the model, and the last date of calibration. All equipment should be calibrated at least annually and certainly in accordance with all the manufacturer's specifications. And some instrumentation, like the tracer gas detector, needs to be tested daily, calibrated daily. So we need to confirm the calibration of the equipment, make sure everything's functioning properly. Record and report these data sheets so that we have the right information to confirm that the data was correct at the time we collected it. Save a lot of issues. All right, moving on to the cross-draft tests. You may not think cross-drafts in the lab can impact the performance of a hood, but they're really quite important because the air being supplied into the space, if you can feel it blowing on you, it's much greater than 100 feet per minute. 100 feet per minute face velocity is about 1.2 miles per hour. So if you were a sailor out on a boat on a lake at 1.2 miles an hour, I'm telling you, you're not going to go anywhere, right? It's a very low velocity. It sounds like a lot in terms of a fume hood, but it's actually very, very low speed. And if you put your hand in front of the hood, you can barely perceive 100 feet per minute. If you can feel the air blowing on you, it's too high. It's going to be much higher than 100 feet per minute. It's also important the direction of its impact on the opening, whether it's blowing vertically past the hood or horizontally past it or directly at the opening. So if we look at horizontal drafts, vertical and perpendicular, those drafts are important for us to measure. So we can arrange our probe. We're using the same face velocity probe, the same velocity probe we're using to measure face velocity. We now pull it outside of the hood, mounted on a stand 8-10 inches outside the sash, and we're going to measure the velocity vector in the vertical, the velocity vector horizontally and perpendicularly, and we're going to do that over a 30-second period on the left, center, and the right side of the hood. So again, left, center, right side of the hood, measuring the velocity vectors, and we're looking to see that it's less than 50% of the average face velocity, ideally less than 30 feet per minute. So 50% is really the cutoff. We start seeing above 50% and we start getting issues with loss of containment. So in this example, we have our probe, this horizontal probe versus the vertical, and it shows it's very turbulent in the left, center, right positions. And when we look at the data from that, we see it range from 36 to 101 with an average of 73 on the left. In the center, it was average 74. And 42 on the right. So our max average was 74. Significantly higher than our 50% of our average face velocity. So that's going to cause an issue potentially with containment. And we look at this turbulence as well. Now, I promise to come back to this example of the cross drafts because of the supply diffuser. Case 1, velocities are blowing directly at the hood. Case 2, we blanked them off to move that air away from the face of the hood. When looking at the average and maximum values of the cross drafts, we see that we're blowing directly at the hood. We saw an average of 76 and the horizontal average of 68 as for vertical. The hood failed to provide that containment. When we blanked off the diffuser, went down to 29, 34, 69% reduction in cross-draft velocities. So that diffuser orientation type diffuser as proximity to the hood was causing high cross-draft velocities interfering with containment capabilities of the hood. We'll show that more detail later. Now, we also want to look at this magnitude of variation. We are taking readings out of the transfer, which allows us to take 30 readings at each location. And when we look you can see the range of turbulence. So this is air impact on the opening. And the hood is trying to overcome that turbulence and maintain containment. But if it's excessive, it's going to cause flow fluctuations, perturbation, flow that cause loss of containment and exposure to the operator. So by reducing the draft, the space for enabling the hood to be more effective and potentially more safe to protect the occupant. So reducing exhaust draft is very important. It also impacts average space velocity. So our next test that we're looking at is the phase velocity test. We want to evaluate how well the airflow is moving through the face of the hood and its uniformity from top to bottom, left and right. And we want to evaluate both the magnitude in terms of average velocity, but also the spatial variation and the temporal variation in terms of that velocity. And so we use a hot wire anemometer. The hot wire probe has heated elements, and that allows measurement of velocities very low values, about 30 feet per minute, and sometimes less. As the velocity moves over the probe, it cools, and then that results in a change in voltage, which allows us to indicate the average space velocity, or the velocity at that period of time. And we want to mount that on a stand, so as to be held stationary at that point in the sash to prevent the error associated with that handheld probe. So that probe, by mounting it on a stand, we use a microphone stand. And then you could use a ring stand and mount it inside the hood. It's up to you. But the standard says that the probe must be mounted at each of these grids. We divide opening into equal areas to measure top to bottom, left and right. And then divide that area into equal areas. It's not more than 1 square feet. So each grid should not have a side more than 12 inches. At the center of each grid, we're going to place the probe to measure the velocity at the center of each grid. And that grid should be in the plane of the sash. So where we have the velocity of the sash, if we were to draw a line from the top sash to the work surface, that is our plane of the sash, and our probe should be aligned directly in the plane of the sash. When you're hand holding the probe, as you are looking at your meter and so forth, you can move that probe out of the plane of the sash and introduce air. And in addition, you need to mount the same location every time because of accuracy and precision. So we want to use this technique of mounting the probe, moving it from point to point across the traverse, so that we increase the accuracy and precision of our measurements, and therefore have better data to use to confirm flow or to verify the operation of the launcher. So again, go back to this. Our integrity is directly linked to the accuracy and precision. We want to collect data that's as accurate and repeatable as possible, so that it can be done by any technician. You go in, you place the probe in these locations, you collect data, it gives you a value, how you compare period to period, and you know that you have consistency from which to judge the operation of the hood. So I'll take 10 to 20 readings in each good location. Instead of one, it may be internal fluctuations. We want to capture that variation so that we can look at the spatial variation and the temporal variation. What is the variation top, bottom, left, and right? That's spatial variation. And then what is the variation in any location? That's temporal over time. So again, we're dividing into equal areas. We're going to measure velocity across the grids. Now, the anemometer that's preferred, that's not specified by ASHRAE 110. It does not mean that you can't use other pieces of equipment, you're just not with ASHRAE 110. A velvet grid is a perfectly good piece of equipment for measuring uniform laminar flow and velocity 60 feet a minute. But when you have turbulence and you have spatial temporal variations, that this instrument is just not appropriate for certification of hoods. It introduces error in your measurements. And so this is appropriate to take the hot wire, not the velvet. Now you can use it for spot checking, and we use it for filter measurements, we use it for lots of different tests, just not our average velocity. Now, looking at velocity variation, top, bottom, left, right. We've got about a versatility of 18 inches, 6 foot hood, so we're going to take, this is 6 by 3 or 6 by 2, and if we look at A1, the top left, F2 is the bottom right of the opening, and in each reading we're taking 10 to 20 readings per location. Now look over here at A1, you can see a lot of turbulence. As we move into A2, that velocity goes up, and it's still very turbulent. And then we move back down here, and we can see across the opening, there's turbulence in each of the spatial, or each of the grids, as well as temporal variation across. So we look at this and we add up, divide by the number of measurements, and that gives us our overall average. So 82 feet per minute was our average, but our range was 73 to 98. Generally, we want velocities to be within plus or minus 20% of our average. Right? So in this case, 80 we could go down 16 one way or the other. Right? And that would give us a uniform distribution of velocity. Now, some hoods are designed for non-uniform distribution. We need to know that in advance. Now, coming back to our situation where we're in case 1, the fuse is loading the hood, versus case 2 where we're wiping off. In case 1, we can see that our variation went from 59 to 96, or a 46% variation, and that's unacceptable. And our velocity was 80 feet per minute, but when we wiped off, it went from 67 to 88, only a 27% variation. And it was a velocity of 77. Now, two things that we noticed is that by wiping off, we had a reduction in the variance of phase velocity, which is going to lead to better containment. But we also had a reduction in average phase velocity because in the first case, not only measured the velocity due to the air sucked into the hood, we're measuring the velocity of the air blowing in the hood as well. And that creates error. It means that we don't know if we're measuring the total velocity or measuring the supply. And so we want to mitigate those cross-drafts to create a more accurate measurement of average. Because what happens if the average velocity is not correct? Right? If it's too low or too high, it issues we're working with. And sometimes we want to fix the hood or repair or something. And if that work order is based on inaccurate measurement, in other words, we made a mistake, we issued a work order, that's wasting time and effort. And it means that we're not going to have the same credibility as if we had done it properly. So using this technique creates the most consistent and repeatable method of measurement so that you can minimize the necessary work that's done to maintain it. There's going to be work for sure. We don't want to create excess work. Now, looking at the impact of those cross-drafts, we can see in case 1, there's a lot of variation here. We had velocities less than 20 feet per minute in some cases because of the impact of those cross-drafts on the open, and you can see how hard it would be for the hood to contain those conditions. In case 2, where we're laying off the diffuser, it's more stable, and so the hood has a better opportunity or better probability of providing adequate containment. And it means that the velocity is more consistent. So we want to eliminate the cross-drafts, get the right average, mechanisms that are operating, the probability of getting the right response. So now, oftentimes the hood test that's occurring now in the lab at that lane massage is compared to the measures that were done by the test dispenser in the exhaust duct. The flow of the exhaust duct must always be greater then the flow of the sash will open. Okay? The reason I say that is because you're going to calculate the average. You use your average velocity multiplied by the area of the opening, and that equals your calculated exhaust flow. But that's the flow of this opening. It does not include the flow of bypass or any leaks in the hood. But the flow measured in the duct is the accumulation of all that flow. It's the flow of the face plus the flow through the bypass. So the flow of the duct should be at least up to 5% greater than the flow measured through the face. If that's not true, if you come in and you measure 100 feet per minute, 10 square foot opening, and you can get 1,000 CFM. But the balance measuring 900 CFM, something is wrong. The flow of the duct has to be greater than your calculated flow, or something's wrong. Right? So that's a very easy check to see to make sure. And we don't know who's wrong at the moment. We just know something. Right? It could easily be a measured flow, or it could be a measured velocity. But we know there's something wrong. Now, if the reverse is true, we measure 1,000 and it's 1,100 in the duct. That's the right value, the right direction. At least we know that then the theory is correct, and it should be closer to reality. So again, just remember, the flow in the duct should be greater than your calculated flow through the face. The calculated flow through the face is only as good as the measurement technique that was used to produce the average velocity. So now we move toward the VAE control and response test. Now there are many different ways for variable volume systems to modulate flow. And it's important now in today's modern systems that we move beyond this measurement of phase velocity. Because measurement of phase velocity tells us the flow through the hood when the sash is open. But what happens when the sash is closed? How low a flow can we tolerate before we lose containment, or we create an unsafe situation inside the hood? Hood can be modulated based on sash sensors that measure the position of sash. They can be modulated by zone presence sensors. They can be modulated by airflow velocity sensors. So looking at these different mechanisms of control, when we first look at a laboratory, a newly installed hood, we'll say, what's the sequence of operation for the controls? What do we expect to occur? And oftentimes we provide a diagram that looks like this. We've got our two hoods, and we notice a lot of instrumentation equipment for the hood. There's a hood monitor, a sash sensor, maybe a blue wall sensor. That's connected to a controller, or that actuates a valve. But it's also connected to the general exhaust and the air supply valves. So my question is, what's happening here? What is our expectation? It needs to be clear. We need to have a sequence that's easy to understand. That says something like the hood modulates flow between the sash being closed and the sash open. And when it modulates flow through the hood, it's connected to the air supply, and it tracks in tandem. You close the sash, the flow goes up. Open the sash, the flow goes up. Should be that simple. A complicated diagram like this may be important for installation and maybe for diagnostics, but it's hard for a hood tester to understand. We need to have an easier description that sets our expectations, and then have criteria. How low can we go? How fast must it respond? What's the maximum flow that's tolerable? What's the impact on room pressurization? These are parameters that we can get around the sequence of controls. So when the sash is open, we've talked about this now several times, the phase velocity multiplied by the area of open equals the exhaust flow. But when that sash is closed, there is no sash opening. You can't measure phase velocity. So how do we know we have adequate flow, and how and who sets that minimum flow? How do we know it's appropriate? Because if it's too low, some bad things can happen. Right? We We also need to have some indication of the monitor. The monitor needs to indicate somebody needs to calibrate it. So what does it indicate when the phase velocity is open? What's the tolerance between the measured average phase velocity and the reported? Is it plus or minus 5% or 10%? If you measure 100 and it reports 100, fantastic. But what if it measured 100 and it reports 89? Is that acceptable? Does it need to be 90 to 110? What is the acceptable range? And then when you close the hatch, there's no phase velocity. So how do you know that it's indicating the appropriate flow? Right? So these are criteria that we need to establish before we start testing the hood to verify that it's operating properly. Now, what's at stake? If the minimum flow is too low, then we're going to lose containment, we're going to have inadequate dilution, and we're not going to remove materials from the hood itself. So sash closed, you can see the accumulation of concentrations. If the flow is too low, it can approach a lower explosion limit, and we could have a bad day, right? Nobody's really happy in the event of an explosion. And it definitely will cause trouble for a whole bunch of people involved, not the least of which is the hood user. So in the 90s, EPA came out with a standard that said 50 CFM per linear foot of hood width. Multiply the width of the hood by the velocity, and that will give you the flow. But in 2004, NFPA 45 said it should be based on the work surface, the depth, and the width. So that was, if you had a 5 feet wide hood by 2 feet deep, that's 10 square feet. Multiply it by 25 CFM per square foot. Lo and behold, you get 250 CFM. But in 2010, NFPA 45 deferred to Z95. They no longer have this criteria. The 95 standard said it should be based on air changes per hour. The width times the depth times the height. That is your internal volume. And now you can calculate an air change rate that is appropriate to dilute and remove the materials. So the recommendation was somewhere between 150 and 375. I'm going to express caution. A lot of people are operating hoods at a flow that is too low. 150 air change per hour may be good for energy consumption, but it's potentially problematic from a safety standpoint and could put the hood into a situation where you get loss of containment or escape, we get poor dilution, and the inability to essentially remove the materials from the hood and the duct system. So that minimum flow is critical. When we look at the airflow control mechanisms, whether it's flow that's being measured or velocity or pressure, every hood should have a hood monitor. How else are we going to tell the operator that the hood's got adequate flow? And it needs to be calibrated using our techniques. And then if we look at what's modulating flow, a through-the-wall velocity sensor has a sensor in the sidewall of the hood, and it's measuring that velocity and reporting the value on the sensor. A sash position sensor is looking at the height or the width of the sash opening, and it's calculating the area and then trying to control to a constant velocity. Then you have occupancy-based. If you have an occupancy sensor, if there's no one there, it's at a lower flow. If somebody steps into the zone, it increases flow. Who makes sure that works properly? And then we have to define the types of operating modes. Two-state. It's either low or high. If it's full VAV, it's modulating incrementally, maybe based on sash position. You raise it another inch, it opens up a little bit more. Raise it another inch, it opens up a little more. That's full VAV. And then you have the hybrid systems. They're modulating flow based on sash position, but they're also looking at occupancy. So when you look at the layering of these controls, the complexities, it makes the job of testing the hood that much more difficult, because now we have to confirm that it operates sash closed to sash open, occupied to unoccupied. And these require different tests to evaluate the operation. So installing VAV controls is a great idea from controlling to a demand-based operation and saving energy when the hoods aren't in use. But if you go too low or they don't control properly, then we can create safety issues that can come back and eliminate any of the value of the energy savings. If the hood's not functioning properly and somebody gets exposed or there's an explosion, the energy savings are irrelevant at that point. We need to be safe first. So monitors are really important. They can measure face velocity, they can measure flow, they can report pressurization. Well, this particular facility